kitty. There, there's the kitty. Kitty popped his head up. Up, there's the kitty. Amanda, look.
Those have to be just as much as before. They're pretty. But anyway, we found that try that. It was pretty.
Test.
I was like, I have not been to and it tastes like.
Doing okay there, Dane?
Yeah, I'm ready to be back. I'm not sure I can have any more quizzes and exams build up.
Fair enough. And labs, yeah.
Yeah, I haven't been to a single full set of labs yet.
Oh gosh. Surely gets old.
What'd you say? I'm sorry.
That surely gets old.
Yeah, it's been a fun time.
We're going to be on this page of your handout for the beginning of today. Really? Every time I go into the Jackson Target, there are lots of African Americans.
Well, it's like a stereotypical like Karen shop at Target.
Okay.
It's definitely marketed towards.
Because you watch your commercials on TV. The commercials on TV, they tend to have rap music.
Yeah, but
The models they have are usually African American models.
but if you look at where Targets are, I thought it was tailored towards like me, I guess, as in like the
Younger.
millennial. There's not a lot of Targets in areas with low income. Jackson has malls, so Jackson has one, but there's not a lot of Targets in low income areas or medium high.
Or in malls. And they tend to be in malls as well. Yeah.
I think it just totally depends on where they're located. Ours are on the border between where I'm from and Troy. It's on the border. But they're definitely a more expensive store. They definitely are. I will give them that.
Yeah. Compared to Walmart or other types of stores.
I would never go grocery shopping at Target. I just found online that they had all that dairy free stuff. I was like, ooh, I'm gonna go. So I was totally surprised. But I wouldn't buy all my like Dollar General from yeah.
Yes, and they tend to drive mom and pop stores out of business.
We don't have any Dollar Generals anymore in my hometown, and my mom's so upset about it. We never did.
Although they can give you lots of merchandise very cheaply,
Yeah, there's.
which is good.
But the problem with they do though is that the return can make their items smaller and put them in for $1. So you're like, oh, it's only $1. But you really.
They're a great place to buy birthday cards.
That is true, yeah. But for food, it's not great.
So my wife will go there and stock up on birthday cards to have birthday cards for everybody.
But they're good because a lot of people have
Dang,
areas.
married person advice. Never forget your wife's birthday. Never.
Oh yeah, no.
Never.
Yeah, were you guys talking about Target?
Don't forget your anniversary either.
Yeah. Were you guys just talking about Target?
Yeah, Amanda's
Yeah.
slightly anti-Target.
Oh yeah, I work there, so.
Oh, Big Lots is like, it's literally the same as Target, but cheaper.
Go to Big Lots. She says it's same as Target, but cheaper.
Oh yeah, Big Lots is good too.
Okay, it's time
I
to.
like Target because they pay me $15 an hour.
Oh, you like Target because they pay him $15 an hour. Okay, ladies, we're going to get started. Let's pray. Lord, we are very gracious for this nice weather. We're so very thankful for the chance to go to school here in person. We don't have to be stuck online. We pray now you'd help us learn about cholesterol metabolism and trafficking and the pathologies therein and the biochemistry therein. It's all really quite interesting, but intimidating. Now, please watch over us in Jesus' name. Amen. Okay, by way of review, remember that the dietary cholesterol and fat is assembled by small intestinal cells into, what are they called?
They're called lipoprotein bodies.
They are lipoprotein particles. Which one?
Chylomicrons.
Dana's right. Chylomicrons. Chylomicrons. Now, chylo is a term in medicine that's used for lymph because they travel through the lymph. So if that helps you remember it, chylomicrons. So chylomicrons then sojourn through the body. They're depleted of fat by an enzyme called lipoprotein lipase, good. Then becomes a chylomicron remnant. It's taken up by the liver. And what protein helps the liver, takes it up?
Is it the E?
ApoE.
Maple
So the
E.
liver has the LRP8. LRP8 is the ApoE receptor. You take up, this is a very high affinity protein for ApoE, but as it turns out, there are, 5 or 6 receptors that can bind ApoE. So ApoE is taken up very, very effectively by the liver. Then,
What's the receptor, the main one?
LRP8 is the main ApoE receptor, but there's lots of other receptors too. There's a protein called Magellan that can bind it. The LDL receptor can also bind it. There's 2 or 3 other receptors that can bind it too. So the liver's got lots of ways to bind that receptor. The fat and the cholesterol is then converted by the liver into a particle called a VLDL, very low density lipoprotein particle. That gets excreted into the blood. It will ferry, F-E-R-R-Y, ferry fat, cholesterol to peripheral tissues. It gets depleted of fat, and it gets depleted of ApoC proteins, in which case it becomes an IDL, an intermediate density lipoprotein particle. Then when it loses a good proportion of its triglycerols and it loses ApoE, it becomes an LDL, a low density lipoprotein particle. The low density lipoprotein particle only has ApoB100. ApoB100 is bound by the LDL receptor. And the LDL receptor is heavily regulated. So there's not a lot of that. There aren't a lot of receptors that bind ApoB100. Pretty much this one. And that's pretty much about it. Yeah. And then the LDL receptor transcription will be decreased tenfold once you get the accumulation of intracellular cholesterol. And then sometimes it's degraded too, which we talked about this protein here, PCSK1. So the pre-protein conversase subtlysin kexin type 9, which is mercifully abbreviated PCSK9. All right, so we're here now with the LDL receptor. So remember, we said this is a member of a larger protein family that's called the LDL receptor family. These proteins all have similar features. They have these clusters at the C-terminus of complement-like cysteine-rich repeats. And this business up here with the negative charges, that's what those are. So these clusters are about 40 amino acids long. They're negatively charged. And they're encoded by this piece essentially right here. That's a signal sequence, of course, that doesn't end up in the final protein. That gets clipped by the signal peptidase in the ER. So there's 7 of these repeats, these 40 some odd amino acid long repeats. Then it's followed by a epidermal growth factor precursor like section that's about 400 some odd amino acids long. And from there, it then has a section that is heavily glycosylated with O-linked sugars. So if there are O-linked sugars, what are they attached to? What are the sugars attached to? Sorry? Right? What amino acids have oxygens in them for attachment?
Cysteine.
Not cysteine, no.
Oh, serine.
Serine, yeah,
That's what I meant. Sorry.
serine.
One of
Sure.
those that connect words.
So they're attached to either to serine or the other one that has an alcohol group in it, threonine. When you have O-linked sugars, and here you can see them here, those dotted lines, those are meant to be the O-linked sugars. O-linked sugars are made in the Golgi apparatus. N-linked sugars, which are attached to asparagine, they're made in the ER. They're attached as a tree. They're made, pre-made, and that whole thing gets attached. That happens in the ER by the oligotransferase. O-linked sugars are attached one at a time, and they're attached in the Golgi by various glucosyl, minosyl, galactosyl transferases, and so on and so forth.
And where are these only sugars mostly resident?
They're located here, this section, this part of the protein that's encoded by exon 15. If we look at the protein, they're right here. This piece here.
Oh, okay.
So there you go, right there. That's your O-link sugars right there. That section is about 60 amino acids long or so. Then you have a single transmembrane domain, a short cytoplasmic tail, and then this short cytoplasmic tail has a sequence an asparagine, a proline, followed by any amino acid, then followed by a tyrosine. This sequence is recognized by adapter proteins. And because it's recognized by adapter proteins, it links the receptor to clathrin-coated pits. So this particular structure that has these different pieces, so the ligand binding piece here, followed by the epidermal growth factor precursor-like protein part here, and then followed by another piece that tends to have sugars attached to it, followed then by a single transmembrane domain, and then a short cytoplasmic tail. These are found in chickens and frogs and sharks and mosquitoes and fruit flies and nematodes. These are found throughout the animal world. Members of this particular family, they all have this particular structure. Very good. So let's go up here now to the ligand binding piece here. That piece there. All right, so this ligand binding domain is very rich in cysteines. It's filled with negatively charged amino acids, and it's very likely that the ApoB100, which has a lot of lysine and arginine residues, will form electrostatic interactions with this domain. That probably explains why you get pretty solid binding between the receptor and this domain. Mutations in this domain will prevent you from being able to clear LDL very effectively and contribute to this genetic disease called familial hypercholesterolemia. There are also inherited versions of familial hypercholesterolemia that actually put a stop codon in the gene sequence right about here. So now the protein is excreted. So now it binds LDL, but that LDL now can't bind any receptor. So it's a dominant mutation that causes inherited high levels of LDL. You treat it with very heavy duty drugs to knock down serum cholesterol levels. Even then, you won't get them down completely into the normal range, but you'll get them close. And these antibody treatments that we talked about before, they can help as well. There's actually also now a gene therapy treatment that is being looked at using CRISPR technology to try and get rid of that rogue allele in the liver.
How does that build up of LDL and manifest?
You start getting plugged arteries very early in life. Normally, plugged arteries take a long time to develop, so you don't get them till later in life, but these folks will get them in their 20s. Okay, so the lysine arginine residues of ApoB and ApoE. They form these electrostatic associations with the ligand binding domain, as we said before. Those are your domains numbered 1 through 4 that you see right here. Those are the main ones. And I think that, yeah. Okay, so as we said, the ApoE receptor is lipoprotein receptor related protein 8, LRP8. It has a structure pretty much just like this, but it's a different sequence. So it recognizes ApoE. ApoE. In the mouse, if you delete the LDL receptor gene, you see that those mice die early in embryonic life. This demonstrates an absolute requirement for this protein. It binds other ligands, not just ApoB100. Also binds ApoE, and then it also binds a protein called RAP, R-A-P, RAP. RAP stands for the receptor associated protein. Very boring name. And RAP is a molecular chaperone that binds tightly to newly synthesized LDL receptor family members in the ER and facilitates their delivery to the Golgi. So RAP is a chaperone and it binds the LDL receptor as well. So the number of receptors on the cell surface, number of the LDL receptors, is subject to ligand-mediated downregulation. Ligand-mediated downregulation. So as you get intracellular cholesterol levels increasing, you get a decrease in LDL receptor transcription by a factor of 10. That is significant. Once in the cell, your cholesterol that you take up will suppress its own synthesis by inhibiting two sequential enzymes of metalonate synthesis, those being HMG-CoA reductase and in particular HMG-CoA synthase. 75% of all LDL uptake occurs in the liver. Other tissues can take up LDL, and they do so. So adrenal gland can take up LDL, gonad can take up LDL, muscle, particularly muscle, skeletal muscle that is repairing, can take up LDL. Skin can take up LDL, but most of it is taken up by the liver. If plasma LDL levels are saturated, so now all the receptors have been removed from the surface, there is a process by which LDL can enter the cell. It's a bulk phase pinocytosis process. That process is not regulated. It is a cell drinking process whereby things essentially just get wrapped by the membrane. There's no official receptor regulation. It's mainly used for taking up liquids. So the membrane will essentially throw a little sheet of membrane around globular water or something like that and just move it in to the cell, essentially. So this bulk phase pinocytosis can cause excessive cholesterol accumulation inside cells. That bulk phase accumulation creates a situation where you have so much cholesterol in cells that is potentially toxic. Let's take a small look at what happens when the LDL particle undergoes receptor-mediated endocytosis. And I don't think I have a picture. Well, I do, but it's way okay. So you'll just have to put up with my lousy artwork. All right, so here is a cell that has the LDL receptor. And remember, this is negatively charged. Let's draw an LDL particle with ApoB100. And on the surface of this, you have ApoB100. And this is positively charged. And that's going to bind to this. Then you have on the C-terminus, remember, you have that NPXY Y sequence here. When the LDL receptor binds to the LDL particle, now you have the assembly on that C-terminus of so-called adapter proteins. Adapter proteins. Oh, I'm out of colors. Okay, so these adapter proteins, there is one that is called autosomal recessive hypercholesterolemia, ARH, which we'll just put essentially like that. And then you get another adapter that binds to it. It's called DAB2. Let's draw DAB2 kind of as a triangle. Now, what do adapters do? Adapters allow for the assembly of this protein called clathrin. Clathrin is a protein that forms a very interesting DAB2. It's disabled. The name of the gene is disabled. The disabled gene was discovered in fruit flies, and it was called disabled because they had legs that didn't form properly, so the flies were disabled. Yeah, it's a D. It's a B. All right, now clathrin is going to form a structure where you have this um, you have this kind of tripartite triskelion. I didn't draw that very well. This actually should come out here. But this triskelion, when it binds to this, it's able to form a cage that deforms the membrane. And so the clacerin assembles on the adaptins. So these are adaptins. And they're going to deform the membrane into a pit. And this pit you pull this together like that, and all you need to do is pull this part of the membrane together, and it'll pinch this off into a vesicle. And this is your endosome. So you pinch this off, the protein involved in pinching this off, you get this protein that forms a ring around this, and it pinches it off, called dynamin. Dynamin is highly conserved, found in fruit flies and other critters too. Pull that purse string, you fuse these two parts of the membrane. You now have an endosome, and the endosome can then fuse with a lysosome. And you now have an endolysosome, and in the lysosome, the LDL can be degraded, and the receptor can be recycled back to the membrane. So as you can see here, mutations in this protein here, ARH, can cause inherited forms of hypercholesterolemia, because that's what ARH stands for. Autosomal recessive hypercholesterolemia. And then DAB2, its partner in crime, aids with this adaptin process as well. Okay, once you get the LDL into a vesicle, the cholesterol esters are going to be hydrolyzed by the acid lipase in the lysosome. Right. So the cholesterol esters get converted to cholesterol and fatty acids. So cholesterol esters, those things in the drawing that look like sea cucumbers. So they go from being sea cucumbers to just being cholesterol and a fatty acid because of acid lipase. Exactly right. Okay. Now, I need to introduce to you a couple of other proteins because they have to do with the genetic disease we talked about earlier. Do you remember vaguely, we talked about this genetic disease called Niemann-Pick syndrome? There are two other proteins involved with cholesterol trafficking that have to do with Niemann-Pick syndrome, and they're in the lysosome. So let's blow up the lysosome. So there's two proteins. One of them is in the lysosome membrane. And this is Niemann-Pick type C protein 1. Niemann-Pick type C protein 1, or NPC1. Then the lysosomal membrane. Then there's a second protein that's actually inside the lysosome. This protein is Niemann-Pick type C protein 2, NPC2. Now, what are these two things doing in the lysosome? NPC2 binds to free cholesterol in the lysosome. So if we make this our cholesterol, it binds it, it then delivers it to NPC1. NPC1 will then pump this not necessarily into the cytosol, but straight pretty much into the ER. And mutations in the NPC1 or NPC2 gene will cause Niemann-Pick disease type C.
The free cholesterol gets pumped where?
From the lysosome into the cytosol, but it usually gets pumped to a protein that will escort it to the ER.
So NPC binds to free cholesterol and NPC1 pumps out.
Yep. And there are several proteins that have been found that will bind the cholesterol and take it to various places. There's also proteins that bind cholesterol and take it to the mitochondria. Because remember, in adrenal gland cells, some of the synthesis of some of the steroid hormones occurs in the mitochondria. So mutations in either NPC1 or NPC2 cause Niemann-Pick disease type C. And in this disease, you get accumulation of unesterified cholesterol in the lysosome that prevents cholesterol delivery to the ER, and it prevents cholesterol delivery to other organelles as well. So this impairs regulation of cholesterol homeostatic genes. So this will cause cholesterol buildup in pretty much all cells. So consequently, it causes a variety of symptoms, as you might guess.
So it causes the cholesterol buildup in the lysosome as well, which directly from the
Right, if you get buildup of unesterified cholesterol in the lysosome. So that impairs regulation of cholesterol homeostatic genes because those genes require free cholesterol in the ER to regulate those genes.
What is the gene called again?
Cholesterol homeostatic genes. That would include the LDL receptor, HMG-CoA reductase, so on and so forth. So you get cholesterol buildup in just about all cell types. So bone marrow and brain are affected, as are the liver and the spleen. So the liver and the spleen will start to enlarge. You get a disruption in bile flow that will cause jaundice. And then because you're affecting the nervous system, you get progressive neurological deficits. So if you have early infantile onset, you will not have the usual milestones. Lifting the head, crawling, there'll be poor muscle tone. Yeah. So you have clumsiness, learning disabilities, and then you have difficulty swallowing, slurred speech, if any.
Can this be have late onset?
It can, there can be a teenage onset. Depends how severe the mutation is. Respiratory failure is the most common cause of death. Treatment is largely supportive. Now, interestingly, in European countries, this, oh crumbs. What did I do wrong? Okay. In European countries, this molecule called megalostat is used to slow the neurologic decline. And we will, sorry? Because FDA is not convinced that it helps enough for it to be approved. Problem is, there's really nothing else that is available. So megalostat will delay neurologic decline. That has been shown. But FDA has kind of, sort of, well, not kind of, sort of, they've just refused to approve it. So this drug, megalostat, you can see it's a modified sugar. It inhibits the glucosylceramide synthase. This is an enzyme that catalyzes the first step in glucosylceramide biosynthesis. So this drug is being used to treat lysosomal storage diseases. And Niemann-Pick disease is a lysosomal storage disease. It's been approved by the European Medicines Agency. It was approved in 2002. FDA has approved it for the treatment of Gaucher disease. Since Gaucher disease results from a inherited defect in the glucose ribosidase, causing storage of glucosylceramide. Miglustat will reduce the number of glucosylceramide molecules, so there are fewer that need to be degraded. The drug crosses the blood-brain barrier. European medicines also approved it for the treatment of Niemann-Pick type C, but FDA has not yet approved it for NPC, albeit it's used off-label. So doctors will still prescribe it. So that's miglustat.
It's crazy, like, how many drugs are used off-label.
Yeah, because doctors talk to each other.
Yeah, like I'm prescribed in the DC medication, and I don't have to use. What does that mean?
If and only if there's a demonstrated risk that exceeds the benefits, and a doctor, you have to prove the doctor was well aware of that. Now, if the doctor just administers things that he or she knows are poisonous. There was a case in New York with this stuff that'll cause Parkinson's, MPTP. And these people would take it just to kind of have a thrill. And one of them who was administering it was a physician, and he administered it essentially to, he figured if they were going to have a thrill, they might as well have it safely. And he lost his license after the police broke up that ring. They were using an illegal substance, MPTP. And yeah. Anyway, okay. So when cholesterol comes in, remember, you regulate those enzymes. And this bulk uptake, as we said, of cholesterol seems to contribute to the onset of atherosclerosis. Well, then let's talk a bit about atherosclerosis. So what happens with atherosclerosis is that you get these white cells that are called macrophages. Now, macrophages have several receptors that can take up LDL. So they have, for example, they have a receptor called scavenger receptor B1. Scavenger receptor B1 is known to be able to bind LDL. It can take it up, and it can take it up quite efficiently. They have another receptor that is called LOX1 that can also take up LDL. And they have another receptor called scavenger receptor A1. That can also bind LDL.
What does LOX1 stand for?
LOX1 stands for lectin-like oxidized low-density lipoprotein receptor 1, which is why I'm calling it LOX1. Lectin-like oxidized low-density lipoprotein receptor 1. All right, now, this is complicated, so stick with me on this. If you have excessive LDL in your body, that LDL has the capacity to make its way between endothelial cells that line the blood vessel. Because it's clear that endothelial cells, in response to damage from turbulence, will breathe a little. They will attach, they will unattach, they'll stretch a little, something like that. And they do that. When they do that, LDL can come underneath the intimal layer. When LDL makes it underneath the intimal layer, it can become oxidized. Oxidized LDL is a chemotactic signal for white blood cells like macrophages. So the macrophages then make cell adhesion molecules in response to that oxidized LDL. Also, the endothelial cells themselves will make molecules that say, it's kind of like they're stepping on a tack, so to speak. That says, because these guys normally are scavenger cells. They scavenge debris, they clean up, they're cleanup crew. All right, so in response to signaling of the oxidized LDL and the endothelium that senses that oxidized LDL, these cells will bind, roll, find their way between the intima into this space between the smooth muscle and the endothelium. They will bind and phagocytize the LDL. This receptor LOX is specific for oxidized LDL. These can bind pretty much regular LDL, but they can also bind oxidized LDL. So the scavenger receptor A1 will bind oxidized LDL, whereas scavenger receptor B1 tends to just bind normal LDL. Now, there's another receptor called CD36 that can also bind LDL. So this thing is armed to the teeth for binding LDL. It's got several different receptors for binding LDL. Now, if it takes up a modest amount of LDL, it'll bind it to lysosomes, degrade it, and everybody goes home happy. If, however, it starts to take up excessive amounts of oxidized LDL, it can't handle that very well, and it gets transformed into a foam cell. And it starts making these pro-inflammatory molecules that recruit more cells into this area. They take up more oxidized LDL. They become foam cells. They make more of these pro-inflammatory cytokines. And you can see what's happening here. You're starting to deposit cells beneath this that become foam cells. And so that layer that lines the endothelium now starts to fill up with, so you're starting to decrease now the diameter of that blood vessel because of all this LDL you've deposited under there. Now, one of the things that this cell will secrete is a growth factor for smooth muscle. Smooth muscle cells will then proliferate, they'll migrate, and they'll form a cap over this. When they do that, you've now made a plaque. And that plaque, if you have a nice cap on it and it's stable, you're not worried about it. But as these cells start to die, they start to release proteases. Proteases now will start to erode this plaque. If you erode this, these smooth muscle cells, they made a bunch of collagen out here. If you erode this then, because of high pressure, it gets up there now in the flow, High pressure is going to erode that cap. You expose that collagen. That's very, very pro-coagulatory. You're not going to clot. The clot fills that vessel. What do we call that? Heart attack, if it occurs in your coronary artery. That's precisely what a heart attack is. If it's in your brain, it's a stroke. If it's somewhere else, it's an infarction.
So if you have a low, what blood cell count?
LDL, low LDL. The chances of this happening are very unlikely. See, there are other factors too, because it's clear that the damage to the endothelium, so inflammation in your vessels, which diabetes causes a pro-inflammatory environment in the vessels. That's why diabetics, your doctor will tell you your LDL has to be even lower than most people. That's why diabetics tend to end up on statins earlier than other people. You might have numbers that are healthy, but the doctor may say, I don't want your numbers healthy. I want your numbers to be super healthy because you've got an endothelium that takes the beating from sugar and other things like that. What if you have high blood pressure? That's also going to cause a pro-inflammatory environment in this, and your vessels or your endothelia are going to be stretching more often as well. You're going to be more prone to atherosclerosis as well. And this condition is called atherosclerosis, and it's due to the subintimal deposition of cholesterol, the generation of foam cells that form these atheromas. So here is kind of this in pathology using slides. So here's the initial intimal thickening. You can see this is with a Sudan black stain that will stain for the fat. You can see you're starting to get this outline of fat, the cells laden with cholesterol. Those are early foam cells. The intima starts to thicken. Then as we can see, we recruit more foam cells. This now starts to invigorate. This is called a fatty streak. Then you get lipid pools. These cells now start to congeal together. Now you can see you're starting to get the smooth muscle cells that are deposited over this. You get this lipid pool. You now have pathological intimal thickening. Here you have a fibrous cap. That's from the deposition of collagen due to these smooth muscles that have moved over like this. And then as time goes on, this can become calcified. And you get a necrotic core. That necrotic core can become calcified, or it can erode this and it can actually pop. And then you get a clot that fills the whole vessel. You know, I forgot to mention one of the other features that increases the amount of inflammation on these cells is turbulence. So you tend to see this occur at places where there's high turbulence. Where do you see high turbulence? Usually branching. Where there's branching, because that's usually where you're going to get most of your turbulence. Okay, so the cholesterol storage in the macrophages explains the formation of foam cells. You can do this in culture. You can take cultured macrophages and you can feed them cholesterol. You can have them take up cholesterol. You can transform them in culture into foam cells. So it's very clear. Biochemically, it is very, very clear that the formation of foam cells is due to constant uptake of oxidized LDL. That's very clear. All right, this then leads us to HDL, which is a regulatory particle. Yeah, so the main cause of foam cell formation is the excessive influx of modified LDL and the accumulation of cholesterol esters in intimal macrophages. Okay, so HDL in all this is the good guy, so to speak. That's why this gets called good cholesterol. Again, there's nothing good about the cholesterol. No, I didn't go out and do community service. All right, so this is a particle that's made by liver cells and also by the intestine. It's made initially as a protein-rich particle. And that protein-rich particle there it is. Protein-rich particle originally is discoid and flat, and then as it matures, it will become more spherical. Initially, it has little to no cholesterol. That's another reason why I find the use of the term good cholesterol just so very highly amusing. Now, these can be formed from VLDLs by the acquisition of various surface proteins. And here is an attempt at a structure of an HDL. Here again, you can see the phospholipid monolayer with the unusual apolipoproteins with their nice two-tone hydrophilicity, hydrophilic side facing the outside, hydrophobic side facing the very fat-loving interior of the particle. The particular apolipoproteins that are specific to HDL. As we said, the nascent HDL is disc-shaped, but it contains these apolipoproteins, apoproteins 1A, A1, A2, has all the apo-Cs. It has apo-D, that's unusual, that's only found in HDL. It has apo-E, and then this enzyme called LCAT, which will catalyze the formation of cholesterol esters from phosphatidylcholine. LCAT, and LCAT is an important enzyme for HDL. Here is the reaction catalyzed by LCAT. How is this different from ACAT? ACAT uses acetyl coenzyme A. LCAT uses phosphatidylcholine, also known as lecithin. So it's lecithin cholesterol acyl transferase, otherwise known as LCAT. You produce cholesterol ester and the lysolecithin. All right, we are out of time on Friday. We're going to see how HDL is a cleanup particle. It vacuums up excess cholesterol from the surfaces of cells. It can vacuum up excess cholesterol in serum. It can also facilitate the transfer of cholesterol from plaques that have already formed. So this particle is very much one of the good guys. If you increase it in laboratory animals, you decrease atherosclerosis. But if you decrease it and increase it in humans, nothing happens. And I will leave it to you to try and guess why. We can talk about it on Friday. I have some theories. Maybe you can chime in and give me some better thoughts on some of my theories. We have Chris Friday.
Basically, this
Yeah.
And then what are we doing tomorrow?
Tomorrow, we're going to take our liver extracts. We're going to re-isolate frataxin using the dynabeads. And just need to make sure we find a roll dynabeads.
Yeah.
Because I looked over the break and I had trouble finding them. I know they're there. I remember we put them in there. They're there. They're probably in a little unobtrusive. I keep thinking they have to be in this big thing. They're probably in some little unobtrusive thing. But I remember us putting them in there. I know they're there. And we didn't freeze them. I know we put them in the fridge, so they're there. We just have to find them. So
Another question, where are you at with homework for this fall?
homework is actually, I picked it. It's being photocopied. I'll give it to you tomorrow.
Okay, and then final question. And last one. In the syllabus, we have a exam next Friday.
Yeah, does that work?
So maybe.
Check your schedules. Then there's a exam scheduled next Friday in the syllabus. Check your schedule, make sure that works,
Okay,
and let me know. We can move it. That date's not holy. So if need be, we can move it.
okay, I'll make sure I don't have a game because we were supposed to have a bunch of games for reserves next week.
Yeah.
Um,
That could be an issue then.
yeah, and then real quick, so my quarantine probably technically ends tomorrow night. I just tested negative yesterday.
Excellent.
I mean, can I come to lab tomorrow morning?
If you want to come, if you feel safe and you feel as though you're not putting anyone at risk, then come.
Okay.
Absolutely come.
Yeah, I'll be there.
Okay. They said they're comfortable with that.
Okay, sounds good.
You tested negative for Pete's sake, so
Yeah,
I think
that's
we're
right.
fine.
Yeah,
Okay then.
sounds good. I'll see you guys tomorrow.
Okay, it's a date.
All right, bye.
Bye.